Okay, hello everybody, welcome to physical science. So now what we're talking about is called gas laws. So everything we talk about now is going to be, I should say everything. Everything we talk about now is going to be fluids, but gases are fluids. Okay, so when you're taking in a breath, you're breathing in a fluid. Okay, so typically your parents might be saying, hey, did you get your fluids today, especially when your second's running up, and you'll be thinking, yeah, I drank Gatorade and water and things like that too. But a fluid is anything that flows freely. So a gas is a fluid, and a liquid is a fluid. Okay, so Archimedes' principle, and if you look in your book on page 81 and 82, there's some pictures that talk about Archimedes' principle. But buoyancy then is, well, Archimedes' principle has to do with buoyancy. And buoyancy is defined as the ability of a fluid, a liquid or a gas, that's what a fluid is, to exert an upward force on an object immersed in it. Okay? So let me explain that a little bit better for you. Okay, physical science, remember, is the introduction to physics and chemistry. So, if you have water, it's a really simple explanation of the buoyant force. You have water, and you make like a cube of the water. Well, that didn't really work out very well. There's a cube of the water. Okay? And it's just like an imaginary cube. But it is water inside the cube. Let me ask you, does this cube of water sink? No, it doesn't. It stays there, right? Well, it's the same density as the water around it, unless it gets changed temperature, it gets too deep. But you never see like a cube of water gone or missing for the water when you look at it on a swimming pool, do you? No, it's always there. So if you can imagine that this cube then is a cube of water in the water, it's not sinking, so it's right there, right? So let me just ask you this: hold a banana in your hand or a piece of tape. If you take your hand away from it, what happens? It falls, right? Now, how do you keep that cube from falling? What do you have to do? Push up on it, right? So you can then say, through deduction, that there is a force that's pushing up on this cube of water that's not falling. Are you following me on that?
Yes.
Okay. So that force right there is called the force subscript B, or the force of buoyancy. And it has everything to do with, and only to do with, the actual fluid that it's in. So, if I would take then, let's say I take a big thing, and it happens to have the same dimensions as this cube of water that I had in the bottom. Okay, same dimensions, same cube. What do you think the force of buoyancy is on that cube? Well, let me ask you this. What would be here in this cube if this cube of this unknown substance wasn't there? What would be there? Water, right? Okay. And so if we go back to looking at just plain water, and we visualize the cube in water, the force of buoyancy is equal to what in this case? According to this cube. The force of buoyancy is equal to the weight of what? Discussion. So this cube of water is not falling. How much do you have to push up on that cube of water in order for it not to fall? However much it weighs is exactly right. So the force of buoyancy is the weight of water, in this case, right? Because I know this cube is made out of water. What do you think? Okay, so I get over here, and I have the same volume of space taken up by the same cube of space, but it's not water anymore. How much do you think the force of buoyancy is in this case? Okay, so the answer is whatever the weight of that object is. Now look at this object. It's big, right? It's got all this extra space up here, therefore a lot of mass. So is this object more or less dense than the water, would you say?
More.
Less.
Less, how come?
Less.
Well, because part of it is out of the water, right? So the force of buoyancy, yes, in this case is equal to the weight of this object, but the force of buoyancy always is equal to the weight of the fluid displaced. Okay, so do you know what that means? So do you know what displacement means? It's what got moved out of the way, right? So if this box here is floating in water, then there's not water there anymore. There's a box instead. But the other parts of the water then are pushing up on that box just as hard as it would be if there was water there. So the force of buoyancy is equal to the weight of the fluid that's displaced. Okay, does anyone have a balloon on them? It is. Okay, so we just looked at a balloon that we made here and we put helium in it, which has 4 grams per 22 liters. 4 grams of helium, okay, 22.4 liters. And then air is going to have mostly nitrogen in it, so it's going to be 28 grams per 22 liters. So what ends up happening is the force of buoyancy pushes up on this by 24 grams per 22.4 liters. Does that make sense? Because if, this 4 grams has to be canceled out. So air is 28, which that's what the force of buoyancy is actually, that's what actually is on that, is 28 grams of air. But now if we're going to talk about the unbalanced net force that causes the mass to accelerate, then we'd have to talk about the leftover force after we cancel out the weight of the air. Okay, does that help you with force of buoyancy and Archimedes' principle? Any questions about that? Okay, so that's Archimedes' principle. Here, this is what you have to remember. Weight of force, the weight of the fluid that is being displaced. And that determines whether an object will sink or float. Now, after you said, if the object is lighter than the fluid displaces, what happens? It floats. And if it's heavier, it sinks. Very good. Okay? Here's a couple other points. If the force is less, then the object will sink. If the force is equal, the object will float. If the force is greater than the weight, it accelerates it upwards like the helium balloon, which is soft. Here's a couple other notes that we talked about. You can write those down. Okay. So now on to Pascal's principle. Pascal's principle states this, and this is not on page 487, new textbook, my fault. It would be though right after page 8182. Pressure applied to a fluid is transmitted unchanged throughout the fluid, or it's transmitted evenly throughout the fluid. Toothpaste, you squeeze on one end, the toothpaste comes out the other end, right? A balloon, you squeeze on one end, it pops out the other end, right? Hydraulic machines move heavy loads. Okay, we'll talk about that here in a little bit. I just want to make sure you understand what I'm talking about here with the principle. So, if you have a balloon, Okay? The particles inside the balloon are moving all directions at all times. Do you agree?
Yeah.
So, and you know, I say all directions at all times, but a balloon like this big is only 6.02 times 10 to the 23rd directions, give or take, right? Because that's how many pieces in there. So, you can say that it's moving there, 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 in all directions at all times. So, if I squeeze on this, right? If I squeeze that balloon down and cause it to have a bigger pressure, then all these particles readjust and they start hitting on each other. You know, if I make the volume a little smaller, they're going to hit on each other more often, right? Well, since they're all like moving at like 300 meters per second, it doesn't take long for my squeeze on this side to be transmitted to all these particles. So these will squeeze out and push against the next ones, which will then hit the, and it's like a chain reaction. It's like the biggest domino effect you could imagine. And all particles that have the same pressure. Okay, and then the next, or what's your, okay, so the whole idea of pressure equals force per area is what these hydraulic machines use. So a hydraulic machine, do you know what it looks like generally? Okay. Okay, so what's kind of handy and kind of neat with this principle is that, you know, all these particles in here are moving around in many different directions. So this, like if I measure the pressure here, it would be the same as here, and here, and here. Now this works in a closed system, so that means that it's not open on either end. It's like everything that's in here. So in a hydraulic machine, this is going to be all liquid. This whole area is one liquid. So the pressure is constant throughout here. So how does this work for hydraulics? Well, pressure is force per area. So if you are looking at this right here, that'd be a circle, right? So there's an area there. So this is a plunger system, I should have said. So here's the stick of the plunger, here's the stick of a plunger. And this has a bigger area. Do you agree?
Yeah.
Okay. So if you look at this formula, pressure equals force per area, and you solve for force, force then equals pressure times area. Okay. Now, if we're looking at how this thing works to our benefit, over here, if we put a force, let's say we put a force here of 10, okay, 10 newtons. So force is pressure times area. Now, on this side, the P and the A are about the same size, right? So that'll give us a force. But on this side, the P and the A are different sides, right? So just by looking at these letters and how they represent numbers, what would happen to the force? Okay, so if I have 10 newtons over here on this side, that's equal to PA. Now, the P in this is constant. That's the whole idea of this principle, is that the pressure throughout this whole entire fluid is constant the whole time. What happens over here to the force? So the force is going to be bigger over on this side. Okay, so how does that help us? Well, the pressure is the same, but the nice thing is this is a machine that we use. So if we only have 10 newtons of strength or force to apply to this plunger, we might be able to get maybe, you know, depending on how big the A is, maybe 50 newtons of force out on this side. Does that make sense?
Yes.
So this is the way a hydraulic system is. Now, just so you don't think we're getting free energy here, there's something else that happens. It's called the force distance trade-off. So if I was going to push this down by 10 meters or whatever amount I want to, then this is only going to go up, like 1. So I don't get as much distance out of it, but I can still do it easier, more easily.
Why don't they?
So we'll continue our discussion tomorrow, and we're going to start with Bernoulli's principle tomorrow, which is a great one. And then, if you want, you can print these notes out tonight or in the library and bring them, and then add your extra notes to them if you like. But most importantly, don't forget the test tomorrow. Okay, have a good night.